So in the back of your spirals, you guys tried this problem over again. Let's see what you were able to do. Then let's go ahead and once it's perfect and it's all worked out, let's go back to our notes one last time. Let's get the nice, perfect, worked out solution on there. But first of all, let's see what you guys were able to do and let's see whether or not it was right. Why are we taking d dx of both sides? Why are we taking it as is? Either you can't get y by itself, which in this case, I don't think you really can, at least not in an ideal way. You can't get y by itself. So we can't make it explicitly stated, so we have to deal with it implicitly. And implicitly says take d dx of both sides, take it as it is. Just go for it as it is. So, the derivative of 3x squared is, the derivative of x cubed is 3x squared. And if you like this better, in thinking about implicit differentiation, you technically could think about him as derivative of the outside, bring down the 3, make the power of 2, keep the inside the same times, what's the derivative of x? What am I doing? I'm peeling off the cubed and saying, hey, there is an x inside. What's his derivative? 1. The u prime, when we're taking the derivative with respect to x of any expression in terms of x, in the silly way the book likes to, and even others, likes to help you remember this, is if these two match, you don't have to worry about a u prime because it'll always be 1. Because inside prime, x prime is 1. Now, what's true though when we go over here to this y cubed? Do these match? No, I'm taking the derivative with respect to x of something of y. So we deal with the y cubed the same way as the y or the x cubed. We start off the same, bring down the 3, keep the inside the same times, to the power of, subtract 1. But then we have to think chain rule. We've dealt with the cubed. Peel that off. What's the derivative of y? 2y dx. Not times 1, if you want to think about it, not times dx dx. When it's in terms of x, it's dx dx, which is 1, no big deal. But y prime, he's a guy. Y prime, he's an actual expression. We put dy dx so that we don't get confused. Now, you guys went over on the other side. You had to do product rule. So, product rule, you did second, d first. Any dy dx? No. Why? Second, you just rewrite, right? d first, derivative of 3x is just 3. If you want to think about it, 3 times 1, whatever. Plus, first, now what? What'd you get? 2y dy dx. I totally agree. Bring down the 2, make it a 1, keep the y the same, times y prime, times inside prime. The variables don't match, the y with the dx, so I need a dy dx. Now, after this, you guys hopefully remembered from yesterday, oh, now what? If you want, you could have made it pretty. The now what question is still kind of out there. I'm just making it look a little bit nicer from
Get dy dx on one side.
get dy dx. And not just dy dx, dy dx terms. That way you don't feel the pressure of having to do all sorts of steps at once. Even though I probably would, but that doesn't necessarily mean you should yet. So then, is it okay if I leave that dy dx? What did you guys do with him? Subtract him over. And we don't just want to get all the dy dx terms on one side, we want to get all the non-dy dx terms on the other. Just move them over, right? So then we have 3y squared minus 3x squared. Okay, I'm going to pause for just a second. How are we doing? Doing all right? Our goal is to get dy dx by itself, yeah? So I'm just moving pieces with dy dx on the left side, pieces without dy dx on the right side. And the purpose is, well, what do you guys see that we could do next? There's 2 different ways of going, and they're both fine.
Take out a 3.
Okay, we could pull out a 3. But what else could we pull out?
dy dx.
We end up with y squared minus 2xy. Is that okay? Now what can we do on the other side, technically?
You're good,
Yeah, since we're pulling out stuff, we may as well pull out the 3 over here too. What happens with those 3's? If you divide, they just reduce to 1. 1 times anything is itself, so in essence, it seems like they disappear. And then if I want to get dy dx alone, divide. Y squared minus x squared all over y squared minus 2xy. Those of you tempted to start crossing off poor little y squareds are killing poor little kids. Remember, you have to be able to factor, or else. Now, some of you are like, well, I could factor y plus x times y minus x. You're right, good job. Make it match, right? If it's a long answer, you just stop there. If it's a multiple choice, well, go looking and see if they factor, but nothing's going to reduce, nothing's going to cancel out. Pull a y out from down here, you have y minus 2x, and that's y plus x, y minus x. None of those factors are the same, so we're done. This is implicit. Yesterday we talked about the steps to implicit. There it is. We did one example. We started another example. You guys just finished this one. Go back to your notes. Some of you in your spirals, I saw you correcting things. Perfect. Great. That means you tried it, you attempted it, something went wrong, and you're fixing it. So now go back to your notes. Take a second. You don't necessarily have to write every single step. Why don't you go ahead and get the solution in your notes, now that you've seen how it's supposed to play out. Before we go on to another example, just take a couple more seconds with this one. In your notes, make it nice and perfect. Does anybody have any remaining questions on the example though, as they're rewriting it, as they're rethinking through it? As you were checking what you did? Or are we okay? Kind of okay. Now we're going to see some extra things today. We are just going to get to practice a little bit more to get the hang of it a little bit more. In practicing implicit, we're practicing derivatives. That's nice. We're going to see a couple more funny things with this section before totally letting you loose for homework due tomorrow. Nice thing though, tomorrow is 0 period too, yeah? So you can work on it as best you can tonight. Come in the morning. And be able to work with your peers on it as well.
Do you have a question?
Yeah.
I come after school and stay like night at the grade where I have to
Oh, yeah.
Okay.
It's just an option for those kids that come in from after school or during lunch or whatever. And there's not necessarily a time limit, it's just are you getting productive work done? And if you're totally caught up on everything, I'll give you an AP multiple choice and have you look it out and see how you do. Alright, are we almost there? See, just a couple of you guys still working. Long story short, implicit. You derive it as it is. No getting y by itself. Take the derivative of both sides. ddx if it's in terms of x, ddt if it's in terms of t, dd something else, dds if it's in terms of s, I don't know. Take the derivative of both sides. Whenever an expression that you're deriving matches the variable that you're taking the derivative with respect to, there's no stress about u prime, it'll always just be 1. Whenever you're taking the derivative of an expression that has a variable other than the one you're taking the derivative with respect to, which you can see down here, then you have to worry about u prime and putting in this case, dy dx. That might change a little bit, but the same idea remains. You're taking the y prime. And then if you get it in multiple places, move them all to one side, factor it out, divide, simplify it, etc. Okay? So what if I was to give you this? No, wrong way. This one. Oh, I want to give you one more. Okay, hold on, pause. I do want to write just a couple of things about these. First, really quickly, technically, we've been doing it all along, but now we need to apply it to harder problems. You've already applied it to a couple harder problems. I have not even still harder, but We have some more examples that we'll look at to hopefully get better and continue mastering this new thing called implicit differentiation, which is alive. But now we need to apply it to harder stuff. So, quick reminder, when we had y equals 5x squared, and when we wrote dy dx, it was kind of like we wrote 1 times, the derivative of y is 1 times, in the sense of bring down the 1 to the power. The derivative of y is 1 times y prime, or times dy dx, equals, and we could say, bring down the 2, then x times 1. Or, if you want to see it a different way, times dx dx. But why didn't we ever write the derivative of x is dx dx, or the derivative of x is 1? Because what happens? Just, in a sense, disappears. It equals 1, and so we never stressed about it. So when we jumped from here to here, we were doing implicit differentiation. We just didn't really think about it. You guys didn't really know you could think about it that way. So anyway, just a quick reminder, we have been doing this in one sense all along. Every time we wrote y, derived is dy dx. The quick remember down below has to do with differentiability and continuity. Remember those snazzy words from our forever card a while ago? There's no real forever card in implicit, maybe there should be, but it's more of just an idea to figure out and be able to apply. So no forever card on implicit. But going back to the one that talked about differentiability, remember differentiability, able to be derived, differentiated, right? Able to be derived or able to be differentiated. This one does a quick reminder. A function is not differentiable when either it's not continuous, or even if it is continuous, when the tangent line would be vertical, or the tangent slopes don't agree as you approach from both sides of a point. And remember in our forever card, we talked about these as occurring when an original function has a vertical tangent line or a sharp point. If a function has a vertical tangent line, if the slope would be up and down, remember that slope is undefined, which means the derivative would be undefined, because derivative talks about slope. And then a sharp point, basically what's going on is your tangent slopes aren't agreeing, and since the derivative is a limit, that's not going to exist either. The derivative is, in its essence, a limit, as we know from the definition of derivative. So, at a sharp point, the slopes are not agreeing as they come in from either side, and we'll work more on that as we get more into graphing. Actually, next chapter? Next chapter. Okay. Wait, that's the one we already did, didn't we? Psh. Okay, hold on. We've seen him way too much today. Let's get rid of him. This one. There we go. More examples. Yeah. There we go. Okay, ready, set. Alright, kiddos. Go ahead and tackle another one. You tackled one at the beginning of class and back of the spiral. We went through, we corrected whatever hopefully you did wrong, if you did anything wrong. You wrote it again in your notes the perfect way. This one's a little different. You're still just taking it as it is, thinking, how do I derive the left-hand side equals how do I derive the right-hand side. Bridget.
So we always use the implicit differentiation every time there's a y and an x?
Every time it's all mixed up. Does that make sense?
So
'Cause-
like, let's say there was a y long and
Well-
it was like cosine x squared and you wouldn't do
Then I wouldn't need to worry about implicit, just take it like normal.
Oh.
But since there is a y alone, but there's a y somewhere else, or even if there wasn't, yeah, we have to go implicit.
Okay.
Oh, just trying to get more space. Haha, I cheated. There we go. So implicit is basically telling you You have the ability to just go without stressing about how messy it looks. You have the ability just to take the derivative of both sides without worrying about what's going on. Real quick, what rule are you guys using on the left? Product or chain? Good. Because it's cosine of, not cosine times, cosine of, right? Derivative of the outside keeps the inside, comes derivative of the inside. Show you a quick trick, just in case some of you get a little overwhelmed in the process. Is what I've written true? Did I take the derivative of the outside? Derivative of cosine is? Keep the inside. Times, what does this mean? Derivative of the inside, but what have I not done yet because this is too overwhelming? I didn't derive it yet, I just set it up. So if it helps you to take a step back and be like, oh, this is gonna be nasty, okay, fine, I'm just gonna say him prime and I'll come back to him next step, equals right over here dy dx. This is a way of not, if you notice that you're forgetting things because you get too wrapped up in one part of the problem and you don't keep writing the rest of it, etc. This will help you just to kind of take a break. Spread out the steps. Now, I'm not done yet. It's time to take the derivative of that little inside. And some of you were just trying to do it all at once, and maybe it turned out just fine. But what rule do we have to use? X times y squared, right? Keep that negative sign of xy squared just as it is. He's fine. I already dealt with him. Times product rule. I'm putting a bracket because a product rule has an addition inside. I need to go ahead and group that whole thing or else I might get in trouble. Second d first, y squared times 1. It's just y squared. Plus first d second. X times 2y. What'd you guys get? dy dx. Nice. There's my product rule. Go ahead and check it out. If you didn't see it was product rule, well, obviously ours isn't going to match. But if you did see it was product rule, do you agree with me? Mm-hmm. Second d first plus first d second. Don't forget the y prime dy dx. Ah, stink, guys. We got to get dy dx alone. Ideas?
No. Nope. Divide by y squared.
Yeah, but if I start dividing by this, you see how he's only in one piece? I could divide this whole. I do want to subtract. I like subtracting, but I can't subtract him. And I can't go subtracting in here because it's tied right now, right? Those are tied together.
Distribute.
I think distributing is probably the easiest. Because I want to subtract. I want to add, subtract, and get everything where I want it to be, but I'm stuck right now unless I undo this distribution. Then I'll have negative y squared sine of xy squared minus 2xy sine. I'm not saying there wasn't any other legal way of approaching it. You might have divided by the negative sign first, but then that just would have been really nasty on the other side. Remember, answers can come in different forms. Bridget.
Can you repeat the minus 2xy sine? Oh, just kidding, I got it.
Oh, yeah, I rearranged and then I multiplied. Good. Now what can I do? It's all adding and subtracting, right? Yeah, move this dy, well, I guess I could. Does anybody not like negatives as much as I do?
Yeah.
Right.
So you could minus the dy dx, or what else could you do?
Minus the
Plus
2x.
the 2x.
Or you could add the 2xy. It's up to you guys, either way. I'm gonna be a little, I don't know, picky and say I don't like negatives, but I could have subtracted. I'm just gonna add the 2xy, sine of blah blah blah. Important blah blah blah, don't mess it up, but I just didn't want to say it. Equals. So I add the 2xy, I'm just making it with the dy dx on the left, because remember equations, a equals b, b equals a, I can put on either side. Who's still stuck on his own?
The y's.
Yeah, negative y squared sine of xy squared. Whew! It's messy, but do you see it? We added this big old piece to the other side, because I don't like negatives. We could have subtracted, but everything's yucky, so I just added. And then I wrote that step here. And then we look at our terms and we say, hey, there's a shared dy dx, so what do we do now? Factor it out. You guys finish them up.
She just wrote
That makes sense, because I just wrote it on there. Booyah! He's almost alone. All you have to do is divide. Whew! Was that intense? A bit, but could you follow the steps? Even if we have like a nasty dy dx inside a product rule being multiplied by something on the outside, it doesn't matter. Try to get it in its simplest form as an addition or subtraction of different terms. So we undid we did the distribution. Then we said, sweet, let's just move stuff where we want it to be. The dy dx terms plucked on one side, the non on the other, and then factor and divide. Do you see how the steps remain the same? Bridget?
Did you get the one by factoring the dy dx?
Yeah. So I pulled dy dx out of both, and remember I have to hold the place when I divide away,
Okay, thank you.
so that when it comes back in, it would still work. And once again, kiddos, this is a derivative that must stay implicit. We're not going to get this thing in terms of x even if we tried. We could do a few things, but not very much. Not very much. All right. Let's go to another more example. A further example, an additional example. Further in. Wrong way. Ooh. Hey, it's a shorter function, right? But pause. Before you start a problem, you should have a plan of attack, and that's something that we need to keep on working on. You need to read the directions, comprehend what they're asking, decide a direction, and go for it. So, when it says find the slope at the indicated point, what are they talking about? Slope of the tangent line, we find that with a derivative, and then after we get a derivative, what are we going to do with that xy point? Go! He's the easy one. Come on, x squared plus 4y squared equals 4. Go find me a derivative, ddx of both sides. No, I don't. I compensate. So, overcompensate either way. Do you hear my voice? It's graveled. My eyes are like kind of happy. Come on, you got him. Compared to the last one, this is child's play. And calculus children. There's this kid on the TED Talk. I think it's a TED Talk. You guys have heard of those, yeah? Yeah. It's like this. How old was he? 7th grader? 8th grader? Doesn't do traditional school, and he already taught himself calculus, and he like did tutoring videos online. Yeah. So he's like, my younger brother's like an astrophysicist. He was a little precocious, a little annoying. Yeah. I think he was like 12 when he made the video. He might have been 10. Wow.
I need to ask you, what was his ethnicity?
White.
Really?
He's just trying to prove the point that if you just do what culture tells you to do and just follow the guidelines, you might be limiting your genius. Something like that.
Thanks.
So he's pretty much saying don't waste time. He was like, yeah, but that's how you spend your time. You don't just. Right? You guys took DDX of both sides, right?
Yeah.
Anyway, look it up. It's a little kid who does calculus. You might get annoyed after a little while, but.
What do you watch Child Genius?
Huh?
My dad used to show me this child card.
I'm not sure if that's my kid.
This was at
You guys got 2x, right?
Yeah.
What happened next? 8y
times dy.
times dy dx. Remember, whenever these don't match, and they don't match, he has y's, he has x's, we gotta have u prime dy dx. And derivative of 4. Some of you are still accidentally writing 4s. 0, you gotta watch out. dy dx equals, hold on, you guys gotta have I heard you. I was talking. Isn't it gonna be negative x over 4y?
That was cringy.
Sorry. There's context and I don't know what it is. That's okay. So, negative x over 4y, true? We gotta subtract and then we reduce, and 2 over 8 ends up being 1 over 4. Okay. We're not done. Okay. I'm finding the slope at the point. I want one slope. This one tells me all kinds of slopes. I need one. If you want to do a snazzy notation, we'll say such that. This is one that we saw last year just a little bit. Derivative such that. We need to plug in the x and plug in the y. Good thing they gave us the x and gave us the y otherwise. So we need to go ahead and solve. And our solving is going to be negative root 2. Struggle. Can we do arithmetic? Can I call that arithmetic? Probably not. Can we simplify?
Yeah.
The numbers without variables, hence why I called it arithmetic. What do we do?
Multiply by square root 2.
Yeah, I like that. Here, I'll write it over here for those of you that are like, it's too far. Negative root 2 over negative 4 over root 2. If you want, you could say the top multiplied by the reciprocal of the bottom. It's negative root 2 divided by the bottom. If you want, you could put a little like over 1, and then you could do like your shortcut. Or you could just, that's only for a select few, or you could say, hey, multiply top and bottom by, we're going to multiply top and bottom by. Yeah, he's that little guy that's just stuck in there, we need to get rid of him. So we're going to say root 2 over root 2. Think of him as over 1. That's the whole point. So then we get up top. Negative root 2 squared. Oh, if only that would simplify and make things pretty. Hey, a negative over a negative, that simplifies, right? To be a positive. Well, that's gross. I guess we should stop.
1/2.
Yeah. Doesn't the square root and the square just cancel? And then we have 2 over 4, and 2 over 4 is just... Well, isn't that pretty? Question. What if they had asked you to find the equation of the tangent line? Y minus y1 steal m equals m. Who would that have been? This derivative or that derivative? This one. So y minus y1 equals m 1/2 times x minus x1. Just saying, if they ask for a tangent line, you know what to do. Bridget, go.
Why is it both positive?
Oh, he wasn't. He was negative, but there's a negative up top too, so I ended up just a negative over a negative is a positive. Or just think they both had negative 1s and both the negative 1s reduced. Okay. Kind of. Uh-oh. We've only been finding what derivatives so far in this section. First derivatives, dy dx, done. Just a hint. on the AP last year. Certain people who like to go by retired football players' names complained about how many second derivatives they were asking for that required implicit differentiation. It wasn't just him, there were others. 2 years ago, a big focus was limits, and everyone was like, limits? What on earth? We're in calculus. Why so many limits? Last year was why so much implicit differentiation? I don't know what it's going to be this year, but I can guarantee you somewhere it's going to be implicit differentiation. And they make it tricky by asking for the second derivative. I even had someone ask me, why didn't you teach us how to do that? And I'm like, oh my goodness, I do. Over and over. Anyway, so it happens every year. We're coming back. And we review, and hopefully it sticks. And for some of you, hopefully it sticks better the second time, or third, or fourth, or 10th. So, we know what this means, right? Who is this? D squared y over dx squared. Second derivative. It has a 2 in there. That's the quick clue. Finding the second derivative implicitly. And I gave you quick steps, which I've actually never done before. I'm actually giving you little baby steps. Derive as is. That means take d dx of both sides. Get dy dx alone. Derive as is again. Why? Because you need the... But the trick is this little piece right here, and that's where almost everyone would get stuck. So let's see if we can just figure out what that second little piece is talking about in step number 2. I gave you an easy function, yeah? Not bad?
Yeah.
All right, go find me dy dx. I'm going to find it really fast, but I'll give you like a 30-second head start. I can't give you that. Okay, so picking d dx of both sides. I was going a little too fast at the beginning. You didn't notice. So did you guys get dy dx is equal to negative x squared over y squared because the 3's reduced? Really?
Sure.
We'll take the shirt. Okay. Subtract the 3x squared, divide by the 3y squared, the 3's go whoop, and we have a negative up top. That's good, but that's not our answer. So what does step 2 say? Go again. Derive again. Derive what again? Derive as is, just go for it. What? Okay. Write d dx again. We're just going. Again, what happens if we take the derivative of the derivative? Look at the d's. It helps you remember d squared y over dx squared. Don't need parentheses, it's all notation anyway, but it helps you remember if you just look at what's going on there. What rule do I need? Ugh. It's okay, go for it. Bottom stays the same. D top, negative 2x. So far, so good. Bottom, D top, minus top, negative x squared, D bottom. What's the derivative of y squared? Yeah, you know that. You just did something similar a second ago. You don't like it, but you know it. All over the bottom squared. What's y squared squared? Y to the 4. Oh, we're done. Box it. No. We have a second derivative over here on the left, but we have this nasty dy dx that's in our way. I'm going to go ahead and do a few things. I'm going to make this look prettier. Negative 2xy squared plus 2x squared y. Question. Why didn't I write dy dx in there?
Plug in better than for it.
Plug in dy dx from step 1.
Yeah.
Step 1 said find dy dx. Who was dy dx?
That one right there.
Plug him in, plug him in.
Yeah.
look. We figure out, we ask ourselves the question, who is dy dx? And we're like, oh, oops, there he is, right? I was going somewhere else. So then we just plug him in, boop, boop. Now the sad story is, we still got to what?
Why work?
Simplify.
You get the y squared.
But we could, wait, can't we get rid of one of the y's, right?
No, we don't do that.
We can get rid of one of them. Now how do I get rid of the nasty little denominator in a complex fraction? Oh my goodness, it's like my summer packet was on purpose. No. To help you with stuff we're going to have to do that have nothing to do with calculus. It's just how to simplify him. And how do we get rid of that little baby y?
Y over y.
Just don't forget your,
You know them.
don't forget your parentheses. What happens when y comes over here?
Negative 2.
Negative 2xy cubed, right?
Wait, did I take out? Never.
Not yet. I could have, but yeah, you're right. I could have learned. If you did, then you'd just be multiplying top and bottom by y squared because you wouldn't have canceled. Plus, no, it's a minus, right? I didn't see that negative guy. Minus, the y's will cancel as I come into my second distribution. The y on bottom and the y up top are going to go ahead and cancel. But I have negative 2x to the fourth, is that right? All over y to the way I did it. So maybe guys, if you had multiplied by y squared, you might just have to factor out a y and then reduce.
You can still do more.
You can pull out a negative and a 2.
Oh, well, if
But like you can't pull out y's, you know what I mean? He doesn't have any.
If you didn't get rid of the y earlier, you could get y cubed plus x cubed, and then make it 1.
You didn't get rid of y earlier, so you would have pulled out a y and that would have been y cubed, but then you would have had to get y squared. I think you would have gotten the same thing. Ella.
Wait, how did we get rid of that y?
Oh, I got rid of one y because there was a y up top and then a y squared down bottom, so I got rid of 1, but there was 1 remaining.
Okay.
So that's how that's why I multiply top and bottom by 1 more y.
You still do it.
Ah.
You pull out negative 2x at the top, and you get y cubed
And
plus x
that is
cubed.
always.
And then if you use the original equation, x cubed plus y cubed.
Okay.
That is always there, but you can never see.
Now kiddos, is this good?
Yeah.
Yes. And of course it's supposed to stay implicit. Of course it's supposed to stay in terms of x's and y's, right?
Bye.
Unless there was a way to keep going. Unless there was a way to keep going. What if we did factor out the negative 2x? We would have y cubed plus x cubed all over y to the 5th. Looking back at the very beginning and saying, look, who is x cubed plus y cubed? This year. Who is x cubed plus y cubed? Oh my goodness. That's what? 1. So then I get negative 2x over y to the 5th. We're only allowed to simplify because that was the original statement that we were given. And if we had this big old nastiness and we're looking at multiple choice answers and they're all way different, oh my goodness, they must have done something. I better start factoring and seeing, oh, that's what they did. Just happened to magically match up. We could technically also solve for y and then plug in for y to the 5th, but ew, that's gross, let's just stop. Okay. There's one more big idea. But you've already seen him. Just now you know how to do him. That's another example. Magic second derivative. We'll save that when we do the warm-up tomorrow. Back to logarithmic differentiation, where you use log properties in order to simplify functions before deriving. What did I put after log properties? You can use log properties.
Bring
And you can even bring in ln. Bring in? Like he's not there? Bring in like he's not there? Yeah. Why? Do you guys see how nasty chain rule would be? Chain rule would be to the 1/3 power, and we have a u within a u within a u. No thing. Doesn't mean it's impossible, but I'm just saying there's another way. We could bring in an ln. We could see this expression as all the nastiness, 2 plus tangent of x squared, to the 1/3 power. And since the entire thing is to the 1/3 power, what can I do with the 1/3? I can bring down the 1/3, and I can ln of 2 plus tangent, I know, hang on. In homework, if it says logarithm differentiation and there's no logs there, you put in an ln, and now you say, what to both sides? Implicit differentiation. What you do to one side, do to the other. We'll see how it goes to the best we can on homework. We might do another logarithmic example tomorrow to start off before going over homework questions. Bye guys. Don't leave trash. Enjoy your PJs. Don't get too hot.
I tried to pull it from right there for you.